I'm Eric Toon. I'm the Deputy Director at the Advanced Research Projects Agency for Energy, ARPA-E. The Electrofuels program is designed to develop efficient means of converting solar energy into stored chemical energy in a liquid fuel that we can burn in a vehicle. All biofuels today rely on photosynthesis, but it turns out this is not very efficient, and only about 1% of the solar energy is captured by the plant and stored as chemical energy that can be converted to a fuel molecule. We're working with organisms that are capable of growing on hydrogen, organisms that grow on hydrogen-sulfide, organisms that grow on ammonia, even organisms that grow directly on electricity. So one of our performers is OPXBIO in Boulder, Colorado. OPX is working on a process using an organism that uses hydrogen with CO2 to produce liquid fuels.
OPXBIO is a renewable chemical and renewable fuel company based in Boulder, Colorado. We have two partners working with us, the National Renewable Energy Lab and Johnson Matthey. We have developed the microbe and the bioprocess using our EDGE technology platform. Early on, we did some work to prove the concept of being able to make renewable fuels, particularly fuels made from CO2 and hydrogen as feedstock. But really our work began in earnest with the award from ARPA-E.
The fuels that we need to make that are renewable really need to be two things. They have to fit with the current infrastructure, so they have to be compatible. And in addition, we really need to make them at a cost competitive point to the petroleum. And that really allows the biofuels or the renewable fuels industry to compete and to grow on its own merits. The OPXBIO has a proprietary technology platform that we call EDGE, which stands for Efficiency Directed Genome Engineering. Traditional approaches can be searching through a very large space of possible changes. What EDGE allows us to do is to scan through all the possibilities simultaneously, identify the important ones that we want to work on. We've also done this and used this process and this technology to optimize microbes that produce bioacrylic. And so the same process can be used and will be applied to the ARPA-E program, looking at how do we get a cost-competitive renewable diesel in as short of a time as it has taken us to produce renewable bioacrylic. So NC State is another collaborator that also is funded by the ARPA-E program, and they have a technology that allows them to convert fatty acids into renewable diesel. And so we've actually been producing renewable fatty acids from hydrogen and carbon dioxide in our fermentations at OPX. So we've actually separated out the fatty acids, which are long chain molecules that are energy dense, and we've purified those, and we're sending the fatty acids to NC State for their conversion to fuel.
We start with a fatty acid, which is, in this case, is solid at room temperature, and we go through a series of thermocatalytic processes. And then if we are going after an aviation fuel, we want some aromatics in there for materials compatibility within the engine. And so we end up with a fuel that's has a high flash point for safety, has a low freezing point because you don't want the fuel solidifying at 30,000 feet. And so this is virtually indistinguishable from petroleum-derived JP8, and that's where we started, what we set out to do.
The United States uses over 12 million barrels of oil a day. Most of that oil is now imported and comes from foreign sources. A significant activity of the United States military is defending the shipping lanes that bring that imported oil to us. So the ability to keep those dollars at home and use those dollars to pay American workers to make the fuels at home is clearly in the economic interest of the United States.